Welcome back, Physical Science 20. This is the FC3.1 mole ratios in chemical equations. So this is the first part of the FC3 stoichiometry section. So we'll be looking at determining the relative number of moles of each substance in a variety of chemical reactions using balanced chemical equations. So we first look at mole ratios. So you can think of a chemical equation being similar to a recipe, with the chemical formulas being the ingredients. So formulas are the ingredients, and then the coefficients in the equation, such as 2, 2, 1, being the ratio of one chemical to another. However, these are the ratio of numbers of entities rather than masses. So the number of hydrogen molecules and the number of oxygen molecules, etc. So for example, this states that hydrogen molecules and oxygen molecules operate in a 2-to-1 ratio. So for every one molecule of oxygen, I need 2 molecules of hydrogen. So this implies that 2 molecules of hydrogen are required to completely react with 1 molecule of oxygen. But what if more hydrogen is present? Then the amount of oxygen required to use up this extra hydrogen is still determined by that 2-to-1 ratio. And the amount of water produced is also determined by that ratio. So if we look at this example here, so oxygen is symbolized using the solid spheres here. Hydrogen is the smaller, we'll go with clear or white spheres, so there we go. And to make a water molecule is made of 1 oxygen and 2 hydrogen. So 1 oxygen and 2 hydrogen. So if we look here, we have enough to make 2 water. Because 1 oxygen molecule has 2 oxygen atoms, 1, 2. And 2 hydrogen molecules has, let's see, 2, 4 atoms. So we have enough to make that. So as you can see here, the way they combine to make the 2 water molecules, 1 oxygen for 2 hydrogens. 1 oxygen molecule, 2 hydrogen molecules. Ditto, ditto, ditto. And that's how we have that using up. So you can see they come together and then make the water molecules. Working with ratios is an essential skill in chemistry. The following analogy describes the reasoning used when we work with ratios in chemical equations. So our ratio analogy, we're going to look at s'mores. So each s'more consists of 2 graham crackers sandwiched between 4 chocolate pieces or chocolate chips and 1 marshmallow. So 2 graham crackers, 4 chocolate chips, 1 marshmallow. And we'll be technical here, make chemical symbols here. So graham crackers, GC, chocolate chips, CC, marshmallow, MM, and a s'more would be SM. So we can think of this as being a reaction involving making 1 s'more from 2 graham crackers, 4 chocolate pieces, 1 marshmallow. So according to that equation, the ratio is 2 to 4 to 1. So 2 to 4 to 1 to produce 1 product. You can make whatever quantity of s'mores you wish, provided that you have these quantities in this ratio. So for example, 4 times as many chocolate chips are required as marshmallows. Similarly, twice as many graham crackers are required as marshmallows. Any ingredient that is in excess of this ratio is going to be left over. So we can do multiple combinations here. If we double the ingredients, we have 4 graham crackers, then we'll need 8 chocolate pieces, and then 2 marshmallows, and that'll make 2 s'mores. And then, of course, we can alter that quite a bit, even as high as moles. If we have 1 mole of marshmallows, then we would need 4 moles and 2 moles to make a total of 1 mole. So we can multiply by any amount, and as long as we keep that ratio, we can use all of them up and make our required product. And of course, one thing to note here is that the total mass before will equal the total mass after. That makes sense because we're just simply putting the pieces together, right? So note that in our s'more synthesis analogy, the sum of the masses of the reactants must equal the total mass of the products, since all ingredients were used up to make s'mores. In other words, this analogy illustrates the law of conservation of mass. Notice, however, that the total number of substances on the left side is not equal. So I have 7 things here making 1. And that's fine because I have those 7 things combining to make 1 product. Okay, if I apply that to chemistry now, so I can look at the synthesis of water, what we used before. So 2 hydrogen molecules combined with 1 oxygen molecule giving us 2 water molecules. So I can just alter that too. 2, 1, 2. So as long as I keep that 2 to 1 to 2 ratio of products, I can use them all up. So this middle one's going to be half as much as the end ones, and you can see all these are that. So 1 mole would mean 2 moles, 2 moles, 5 moles would mean 10 and 10, etc. So as long as we keep that ratio, we're fine. So note that in each set of quantities, the ratio is 2 to 1 to 2, as illustrated above, given by the coefficients in the chemical equations. In fact, each set is a whole number multiple of coefficients 2, 1, 2. This ratio is valid whenever you're considering a few or even a large number of molecules or particles. The ratio of the amount in moles of one chemical to another in a chemical reaction is called a mole ratio. The mole ratio can describe the ratio of reactants required to react. It can also describe the amount of product expected from given amounts of reactants. The mole ratio is related to the coefficients in the chemical equation. So determining mole ratios, you've seen how the amounts of reactants or products in a chemical reaction are multiples of the coefficients of the balanced chemical equation. Whole number multiples are easy to predict, but what if they are fractional multiples, as we'll see on the next page? So if we look over here, example, determine the mole ratio, or determining mole amounts using mole ratios. What mole amount of hydrogen is produced if I have 5.2 moles of ammonia decomposing? So I like to put mole amounts on top of the equation here, as you'll see when we move on. So according to this, my mole ratio of the 2 items that I'm concerned about is ammonia and hydrogen. And if I look here, it's a 2 to 1 ratio. 2 moles ammonia to 3 moles of hydrogen. Okay? Now, I could state that in another way, too. I could state it in terms of 2 moles of ammonia compared to 3 moles of hydrogen, or 3 moles of hydrogen to 2 moles of ammonia. So if I'm starting off here, I'm going to want to go from figure out how many moles of hydrogen I have when I have this, knowing that it's a 2 to 3 ratio. So if I start off with my 2 moles of ammonia, so what I'm going to do is convert that to moles of hydrogen. And I can see that the ratio that I will be using is going to be this one right here. Because I have 2 moles of ammonia on the bottom, which of course, it'll cancel with that, and leaving the 3 moles of hydrogen on top. Well, my 3 got a little weird there. On top. So 2 to 3. So starting here and going to here, 2 to 3. Start, finish. Bottom is the start, top is the finish. So when I do that, I get 7.8 moles of hydrogen. So that's how we do it. That's how we can use the mole ratios to go from one substance to another. Let's look at another one. A freshly exposed surface of aluminum quickly reacts with oxygen to form a layer of aluminum oxide. What mole amount of oxygen is required to completely react with 6? Now, I think I have a mistake here. I think this is supposed to be, now I'm not sure, your sheet may not have it, but this should be -2 here, because that's a huge amount we're talking about. So it should be 6.4 times 10 to the minus 2, if yours doesn't already say that. And we're going to be going from here to here. So of course the mole ratio here, we have 4 moles of aluminum compared to 3 moles of oxygen. So I'm not even concerned about the aluminum oxide. I'm just concerned about the substances that I'm trying to find out and the substance that I'm given information for. So starting off with this, 6.4 times 10 to the minus 2 moles of aluminum. And of course I know I'm going to be going from moles of aluminum to moles of oxygen. Moles of aluminum to moles of oxygen, because yes, I'm going to want to cancel this unit. So of course, that involves this ratio. So 3 moles of oxygen is required for every 3 moles of aluminum. And of course I can cancel off there. And I get 0.048 moles of oxygen. There we go. There we go. One more before the assignment. Phosphorus, P4, burns in oxygen to produce diphosphorus pentoxide. What mole amount of oxygen is required to produce 0.25 moles of the product? So of course, here we have our product. Here we have our reactant. So yes, 0.25 moles. So this time we're starting here, but that's okay. 5 moles to 2 moles. So the ratio here is 5 moles of oxygen to 2 moles of phosphorus pentoxide. Or I could just reverse that around. To 5 moles, 5 moles of oxygen. So starting off here, this time I'm starting off with this. Now you can start off with product, it doesn't matter. So if to get 0.25 moles of P2O5, and I want to figure out how much oxygen I would have required, 2 to 5. 2 moles of P2O5 is produced for every 5 moles of oxygen used. So yes, I'm using this ratio this time. And of course, you know, if you're doing it right, if you can cancel. So always do this little canceling part here, because if you can cancel, that means you're doing it right. 0.625 moles of oxygen is required. If I go to 2 sig figs though, that's a 5. So that's going to get bumped up to be 0.63 moles of oxygen. All right, that's it. So you should be able to do the assignment for that, FC 3.1, and we'll see you again.